At the beginning of the year, we talked about a lot of the questions that calculus can answer that the math from pre-calc, geometry, algebra, whatever, has not been able to. And then we spent several chapters talking about how the derivative gives us the instantaneous rate of change, and then looking at a lot of applications of rates of change. So in the second part of calculus, we look at what we can do if we kind of go backwards through that, where we can accumulate. And so what we're doing now is just kind of connecting those two ideas, or moving from the idea of rate of change to see what that tells us about amounts. Okay, so 6.1, actually I'm kind of putting 6.1 and 2 together here. So 6.1 is just the idea of looking at accumulations of rates of change and what we can conclude from that. And then we are going to look at how to approximate values of those accumulations. Okay, so let's look at a couple examples here. We have a graph here, and it does tell us that it's the derivative. So this is the graph of f prime of x. We don't know what f is. And we do know, though, that f of 0 equals 0 and f prime of 0 equals 1. Okay, so if this is the graph of f prime, that's telling me that right here I have a height of 1. Okay, and then we want to know which of these three statements are true. And it looks like we're comparing values of f. But again, we don't have a graph of f. All right, what we do know is that at 0 on the graph of f, we have a point at 0. And then we also know that the slope is 1. So I'm just going to put a tangent segment through there. Okay. So between 0 and 1, f prime is positive, and it decreases down from 1 to 0. So I have a slope that is positive but decreasing to a slope of 0. So we'll call this 1. Okay, so if I want to compare f of 0 and f of 1, I don't necessarily know what the value of f of 1 is, but I do know, because f prime was positive, that it has to be something bigger than 0, which was f of 0, so I know that this cannot be true. Okay, in the second statement, we're comparing f of 2 and f of 1. I know between 1 and 2 that my derivative is positive. Okay, that my derivative is positive. My derivative is not only positive, but it increases back up to maybe a little bit more than 1, and then decreases back to 0, but it's never negative. So we have a slope that increases up to maybe 1 point something, and then decreases back to 0. So we could have a graph that of f that maybe kind of looks like this. All right, so f of 2 has to be bigger than f of 1, because f prime is positive on this interval, so the function was increasing. Okay, so this one does have to be true. And then lastly, we're comparing f of 1 and f of 3. So on the interval from 2 to 3, the derivative is slightly negative but decreasing, meaning that our slope is from 0 and then decreases, maybe just barely, but something like this. Okay, we'll call this 3. So because the derivative is negative, that tells us the function is decreasing. Okay, so comparing f of 1 and f of 3, well, it kind of depends how we drew the graph, because right now, the way I drew it, it looks like they're about the same. Okay, but here's the thing. First of all, the question says which must be true. But secondly, we want a way to compare the value of f of 1 and f of 3 without having an equation for f, okay? So this is what we need to consider. Between 1 and 2, we increased and accumulated, okay? So think of it like we're picking up this amount of space. So if I want to compare f of 1 to f of 3, I need to know, is this amount of space, okay, is that amount of space the same as this amount of space? Is it less than? Is it more than? Because this tells us how far down our function went, and this tells us how far up our function went. Okay, and this does look to be like it's a larger area than this one right here. Okay, which makes me think that it increased more than it decreased. So really, maybe a better picture here would be something that's not quite so negative. Okay, and so is f of 1 going to be greater than f of 3? I don't think so. It definitely doesn't have to be true. So this one is out, and our answer is B, 2 only. Okay? So again, what we're doing here is we're kind of comparing the amount of space that has accumulated here compared to the amount of space that has accumulated here. Okay, let's look at another one. Motion, as we know, is a very common application of calculus concepts like derivatives, rates of change, that kind of thing. So let's look at this one. So we know that a particle P moves along a straight path with a constant velocity. Okay, so the velocity is a constant of 2 feet per second. So this is the graph of the velocity of that particle. Okay, and this is just going to go forever. And it's just like the line y equals 2 because, again, it is a constant 2 feet per second. This is my t-axis, this is my velocity axis. So the question says, what's the total distance the particle traveled from time 0 to time 2? Well, if we think about this for a second, we know that if we are walking 2 feet per second, over the first second we've gone 2 feet, and over the second we've gone another 2 feet. So we know that that's going to be a total of 4 feet, okay? But let's see how that's represented in the graph. All right, in the graph, over the interval from 0 to 2 feet, we see this 4 feet represented because it's the amount of space that is accumulated under that line, the velocity equals 2. Okay, and this is just a 2 by 2 square, okay, and the area of that square tells us the total distance that the particle traveled. All right, if we wanted to know how far had the particle traveled over the first 4 seconds, okay, well then this would continue, and we would continue to accumulate area, and we would say 4 times 2, it will have gone 8 feet, okay? Another thing I want you to think of is what we're essentially doing here is we are multiplying our 2 feet per second, pay attention to how I'm writing the units here, 2 feet per second times 2 seconds, and ending up with 4 feet, okay? This is a rate, okay? And when we accumulate that over some amount of time, we end up with an amount, okay? And that's kind of the idea that we're getting towards here is how can we use the graph of a function that represents a rate of change to tell us something about an accumulated amount, okay? Let's look at another one. So for this one right here, we've got Sir Isaac and the Newtons, okay? They release a single, and this graph shows the rate of the number of downloads per week, okay? So d of t is a rate function, okay? Here's an important word here. And it's a rate of the number of downloads per week, so downloads per week, okay, in thousands. And the question is, how many total downloads were purchased during the 10-week period? Okay, pause it, try it, see if you can figure it out, and then resume. Okay, so over the first 4 weeks, well, actually, let's just look at the first week. In the first week, there was a constant rate of 3,000 downloads per week, okay? So in other words, 3,000 downloads happened during week 1. During week 2, another 3,000. During week 3 and week 4, another 3,000, okay? So what we see is the area right here represents the total number of downloads over the first 4 weeks. So we have 3,000, 3,000, 3,000, 3,000. So far, over this time, we have a total of 12,000 downloads, okay? And then the rate of download slowed. The song was still being, the single was still being downloaded, but not as quickly, okay? It had a decreasing rate, and so we are accumulating this space, but not quite as much as before. Now, looking at this shape, actually, let me clear those off. Okay, looking at this shape, this is a trapezoid. We do need to remember the area of a trapezoid, so let's refresh on that real quick. The area of a trapezoid is the average of the bases, b1 plus b2 over 2, times the height. Okay, and we'll get a little more into that later. But so I'm looking at a trapezoid. Turn your head sideways if you need to. So the bases are 1 and 3, and then the height here is 2. Okay, that distance is 2. So we have 1 plus 3 is 4, divided by 2 times 2. So there's 4,000 downloads that happened during that amount of time. Okay, and then we have another trapezoid because now the song gets more popular, so the rate of downloads increases up to 9, and so now I'm looking at a trapezoid with a height of 1, 2, 3, 4, and then bases of 1 and 9. So 10 over 2 times 4. Let me add these all together. Okay, so 10 over 2 times 4 is 20. Okay, so another 20,000 downloads in those last 4 weeks. Okay, so our total number of downloads is 12 plus 4 plus 20, so 36,000 downloads. Okay, so are we starting to see how the accumulation of the space under a function, okay, will give us an amount of whatever it is that is being accumulated? Okay, now in example 2, we had a constant function. The particle was moving at a constant velocity of 2 feet per second. Okay, but let's come back to that and let's see what happens if maybe it's not a constant velocity. Let me change the window here. There we go. Okay, so a new particle, Q, moves along a straight path. I don't know what the word width there here is. Just ignore that. Okay, the graph of the velocity of particle Q is shown. So here's the graph of the velocity of Q. Okay, and so we do have a function for it. The velocity of particle Q at time t is 0.5 t squared plus 1. We are now looking for the total distance the particle travels from time 0 to time 2 second. Okay, we are going to approximate this amount. We've already talked about how there's a relationship between the amount of area that is under the curve and the amount of, in this case, distance that is being accumulated. Okay, but on the previous example, the function was constant, and then here the function is not constant, but they were still linear, so we were still able to use geometry to find those areas. We are going to use geometry to approximate the areas here, and the easiest shape to find the area of is a rectangle. In fact, all the other areas are based on rectangles, so we are going to use rectangles to approximate this amount. Okay, we are going to do this first by using what's called a left Riemann sum. Okay, say this word out loud, Riemann. Okay, you didn't say Ryman, right? I hope not. Okay, so this is a Riemann sum, and a Riemann sum, the idea of Riemann sum is just the idea of taking an interval, okay, and partitioning it into subintervals, and then using those to get areas, or to find rectangles, and then using the areas of those rectangles to approximate the total area that is under a curve. Okay, so we're going to start with a left Riemann sum. A left Riemann sum, that means we are going to use the left endpoint of the subinterval to get the height of the function, and therefore the height of the rectangle. So I'll show you what I mean. On this first graph, I'm going to use one subinterval, meaning I'm going all the way from time 0 to time 2. And I'm going to use the height of the function, so where my curve intersects the line x equals 0, and I'm going to turn that into a rectangle. Okay, so this is the rectangle I'm using, and I know that my area right here is 2. Okay, so that total area is approximately 2. Now, I can see that that's definitely an underestimate, but that's what I would get if I used the left endpoint. Okay, so let's think about how we can make this more exact. Well, for part B, it says now use 2 equal subintervals. Okay, so I'm going to come to this second graph. Now I'm going to use 2 subintervals, okay, and it says equal subintervals. If my interval goes from 0 to 2 and I want 2 subintervals, that tells me that I should split the subintervals at 1. So I have subinterval from 0 to 1 and a subinterval from 1 to 2. Okay, so if I'm still using a left Riemann sum, then I take the left endpoint of the subinterval, and the height of the function at that point becomes the height of the rectangle. But now I've got a second subinterval, and so the height of the function at the left endpoint here at 1 becomes the height of the second rectangle. Okay, so already we can see that we are a little bit more accurate because this amount of space right here was not included on our first estimate over here. Okay, so we know that we're getting a little bit closer. So let's go ahead and do this. So here are areas approximately, and so for my first rectangle, it's a 1 by 1. My second rectangle has a width of 1, and it has a height of f of 1. Let's figure out what that is. And so f of 1, let's go back to the original function, would be 0.5 times 1 squared, so just 1/2 plus 1. So that's 3 halves plus another 1. So 5 halves is the estimate for the area now. Okay, and hopefully what you're noticing is, hey, we can get even more accurate if maybe we increase the number of rectangles or the number of sub intervals that we use. Like what if we used 4 instead? Okay, another option is we can use something other than the left endpoint to find the height of the function. So for example, let's say I use the right endpoint. So for part C, it says use a right, or find a right Riemann sum with 2 equal subintervals. So I'm still going to go from 0 to 1 and from 1 to 2, but now I'm going to use the value of the function on the right end of the curve, or of the subinterval, the height of the curve there, to get the height of my rectangle. So now I'm looking at this rectangle and then at this rectangle. Okay, so if I estimate that, so this is for part C, my area is approximately 1 by, and then this has a height of, we just said that that was 3 halves, plus, and then the second subinterval, again, has a width of 1, but it has a height of 3. So now we have 3 halves plus 3, which is 6 halves, so 9 halves. So now we have another approximation for that area using the right endpoints. Okay, so let's talk about these. This one, definitely an underestimate. This one was better, but still an underestimate. This one is an overestimate because now we can see this space, get rid of these, this space here that we are accounting for in our approximation, but it is not actually under the curve, okay? So you might be thinking, well, what if we did a left Riemann sum and a right Riemann sum, and then maybe average the two of them, found what's halfway in between those? That would be a much more accurate approximation. Okay, which is what we're kind of talking about here, is how can we make the approximations more accurate? So we could do two, like a left and a right Riemann sum, and then average those. Another option is we can increase the number of rectangles. So imagine like that. I'm just going to kind of sketch that same curve again. Okay, imagine if we did, I don't know, let's say 8 rectangles. So there's 4. All right, and this is a very rough sketch here. But what if I had one rectangle, and I'll use left Riemann sum. So one of them's here, one of them's here, one of them's here, 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 here. These are the heights of the rectangles. So now there's much less space. It's still an underestimate, but there's much less space that is not being accounted for, okay? So our idea here is we make the approximation more accurate by increasing the number of rectangles that we use, okay? One thing that we need to consider when we are using these approximations, though, is we sacrifice some efficiency for accuracy, and sometimes it's about kind of finding a balance between those two things. So on this one right here, yeah, that would definitely be a lot more accurate if I use 8 rectangles and 8 subintervals instead of 2, okay, or even 1. But now I have to find the area of 8 different rectangles. The width of each rectangle, or the length of each subinterval, I'm going to call that delta x because it's a horizontal change. That would be 1/4, okay, because we're going from 0 to 2, and I cut it into 8 pieces. So each one would have a width of 1/4. But then the height of the function, I would have to know what is f of 0, what is f of 1/4, what is f of 2/4, which is 1/2, what is f of 3/4, what is all the way to what is f of 7/4, okay? I would have to find all 8 of those values by plugging them into this function, and that can get a little messy, especially if we're trying to do that by hand. So sometimes it is easier just to say, hey, we're just going to use 2 or maybe 4 rectangles, and we know we're not going to be super accurate, but it is going to be a little bit more efficient. In part 2 of the video, we're going to talk about 2 other types of numeric approximations that are going to be a little bit more accurate than a left or right Riemann sum as well, and will also be part of the ways that we need to be able to approximate.